Okay, so this is the problem number one for this tutorial, which is on topic 8, failure. A specimen of a 4340 steel alloy having a plane strain fracture toughness of 54.8 megapascal under root meter is exposed to a stress of 1030 megapascal. What will this specimen experience fracture? Fracture if it is known that the largest surface crack is 0.5 millimeter long. Why or why not? Assume that the parameter y has a value of 1. Okay, so for the solution of this problem, we can consider that. So we can consider this equation. Kc is equal to y sigma c under root pi a. Okay, so where Kc is the fracture toughness, sigma c is the critical stress. So using this equation, we can input these values of the fracture toughness, which is given as 54.8, and the value of y is 1. So we can find the critical stress pi, and the a is the surface crack length, which is 0.5 millimeters. So we can convert it into meter by multiplying it by minus 3. So if we will solve this equation for this critical stress, then we can find that the answer will be 1382.67.7 megapascal. So this is the critical stress value. However, in this case, the applied stress is 1030 megapascal. So since applied stress is less than the critical stress, therefore our conclusion is that no fracture. What we need to find is that will the specimen experience a fracture? So our answer is no fracture will occur. Problem number 2. Exercise 2. A structural component in the form of a wide plate is to be fabricated from a steel alloy that has a plane strain fracture toughness of 98.9 megapascal square root meter, and a yield strength of 860 megapascal. The flaw size resolution limit of the flaw detection apparatus is 3 millimeter. If the design stress is 1/2 of the yield strength and the value of y is 1, determine whether a critical flaw for this plate can be detected. So as before the previous problem, we have this equation again. So Kc is equal to y sigma c under root pi a. So the fracture toughness Kc value is given 98.9 megapascal square root of m. Y again is given as 1. Here we have the yield strength of 860 megapascal. So yield strength is actually the critical stress value. Okay, so but this critical stress value of 860 megapascal has to be limited to 1/2 of the value. if the design stress is 1/2 of the yield stress, so this critical stress value will be limited to 1/2. So in that case, what will be the crack length? Okay, although the this value for the flaw detection apparatus is given as 3 millimeter, but this is the minimum value which can be observed. The meaning of that value is that. So what is actual length of the straw, length of the crack in this case? So from here, just solve this for the value of A using your calculator. So you can find that this value will come out to be 0.0168 meter or 16.8 millimeter. So as you can see that this value of the crack length is much bigger than the resolution. So this means that this crack can be definitely detected, because 3 millimeter is the minimum value which can be detected. So the answer is can be detected, because the crack length is greater than the resolution of crack detection apparatus. So the next question is a 6.4 millimeter diameter cylindrical rod fabricated from 2014 T6 aluminum alloy is subjected to reverse tension compression load cycling along its axis. If the maximum tensile and compressive loads are 5340 Newton and minus 5340 Newton respectively, determine its fatigue life. Assume the stress plotted in the figure below is the stress amplitude. So we need to first find the stresses. Okay, so these are the maximum. This load is is related to the maximum stress. So sigma max is equal to 5340 Newton is the load divided by the area, because the diameter is 6.4 millimeter, so it will be pi by 4 into 6.4 millimeter means 0.0064 meter. Okay, and then if I multiply it with 10 to the power 6, so then this will be the Newton per square meter, and then if I multiply it with 10 to the power 6, then it will be megapascal. If it is the Newton per square meter, that is the Pascal, and then I need to divide by 10 to the power 6, then it will be the megapascal. Okay, so anyway, I will calculate it. So this figure will be 166 times 10 to the power 6 pascals, or it means that it is 166 megapascal. So now I can see this 166 megapascal line from here. Well, remember that the values are given as the stress amplitude, not by the maximum stress. So we will assume that the graph given over here is for the stress amplitude. And then the other one is sigma minimum, that will be minus 166 megapascal likewise. And we know that the stress amplitude, that means sigma A, is equal to the sigma max minus sigma min divided by 2. So it is actually 166 minus 166 divided by 2. So basically it will be 166 megapascal. So we will be looking at 166 megapascal value over here. So this value will be somewhere here, and then this will touch it over here. So therefore what we need to find over here is the if the maximum tensile and compressive loads are this, respectively determines fatigue life. So as you can see that the fatigue life is approximately 10 to the power 7.